today is kind of back up before what I'm trying to get to. What I'll go over more next time is start to get more into issues about quantum field theory and really try and understand how symmetries work in quantum field theory. And so how do symmetries work in quantum field theory? But what one of the main points of this class was really to set up the formalism in finite dimensional quantum mechanics and the formalism for the harmonic oscillator in a way that would generalize very straightforwardly to quantum field theory. So before we so I'll start to get into that at the end of the class today, and we'll do more about it next week, next Tuesday. But I thought what I'm going to do today is kind of go back and kind of do a quick overview of this earlier stuff about how to about quantization and the harmonic oscillator and quadratic operators, and kind of set this up and to show you kind of how to think about that in a way which is going to generalize nicely to this quantum field theory case. Okay, and so in the usual way of doing okay, so maybe again for those of you who have had more of a conventional class in quantum field theory, let me say the usual story. So the usual story about symmetries is you start with a Lagrangian, and you have and you notice that it's invariant under G, especially a Lie group G. And then what you do is you then use use Noether's theorem. Use Noether's theorem to show that if you've got a Lagrangian that's invariant under group G, then for each element of the so X, for each element of the Lie group, you're going to of the Lie algebra of the Lie group, you're going to get gives a conserved quantity. And then what you do it, and then you're going to quantize, and you get your symmetry operators. And they commute with the Hamiltonian. Okay, so this is the general story about kind of symmetry. You get that the way it's more normally explained in a quantum field theory. You're going to start out with the Lagrangian functionals on fields, and you're going to notice that there are groups acting on them. Then you're going to use this Noether's theorem to get some certain functionals of the fields. It's one for each element of the Lie algebra of the group, and then you're going to take these guys and somehow quantize this and produce operators, perhaps by canonical quantization, and then these operators are going to these operators are going to commute with the Hamiltonian, because they're really just kind of by Noether's construction, these are conserved in the sense that they stay the same. If you evolve according to the equations of motion, which are the Euler-Lagrange equations, these things are conserved. So when you quantize, they commute with the time time evolution, which is generated by the Hamiltonian operator. So that's the normal story. But what I want to try to do is instead here for us, the way I set this up was to not start with a Lagrangian, which is defined on configuration space, but to start with a phase space, or M, if you like, or the phase space or the dual phase space, and it's got a Poisson bracket on it. And then what I showed was that for each okay, so then what we showed is that there's Or actually, and I'll say this for the bosonic case, but I could make a very similar statements for fermionic variables at all points. And so, for instance, instead of starting with a Poisson bracket, which is I could start, which is defined by an antisymmetric, an antisymmetric two form. I could start with a symmetric two form and do fermions. But let me just say it for bosons. But if I say it for bosons, then I've got a what happens is that this. So this is R2D, and then you have a SP2D R symmetry. So they're the subgroup of invertible linear transformations that act on your phase space, but that preserve the Poisson bracket is kind of by definition this symplectic group. And then for X, this element of the SP2D goes to here the crucial construction is something I called UX, which is the moment map. And what this is it's going to be a quadratic function it's a quadratic function on phase space, or a quadratic polynomial, or it's just a homogeneous quadratic polynomial. So this is just some kind of thing that's quadratic in P's in P and Q's in P and Q's. Okay. So this is the kind of general story, but then the and then the idea is that we're then going to do we're then quantize. Well, then do what? So then do canonical quantization, which for us is just we have this kind of one representation of the short one up to unitary transformations. We have this one representation of the of this kind of Heisenbergly algebra, which is given by the coordinates on here, and we just use we figure out how to generalize the action of the P and Q operators to actions of quadratic things in the P and Q operators, and then we're done. So it's a little bit similar. So this part of the story actually. So typically, what happens in the when you do this is you end up with some kind of conserved quantity which is written in terms of Q and Q dots. So you have to do some kind of Legendre transform to get it in terms of Q and P's. But then what you get there are many cases in which you're going to get the same. You can get the same. So especially if you have it. There are many cases in which you're going to get this. You can do the same thing this way, or you can do it this way, and you'll end up at this point here. If you re-express these things in terms of P's and Q's, you end up with these guys. One of the interesting things about this method is that it generalizes, and you can get more. I mean, you actually have a kind of bigger, and you can get kind of interesting operators this way, which you don't really see from this process. But anyway, but this is what we're doing. And so then the other part of the story is Bargmann-Fock. So in order to do this canonical quantization, you have to figure out some way in which you're actually going to construct your operators and states. And I mean one way to do it is just a kind of the Schrodinger quantization to quantize by looking at states as functions on configuration space and look at operators. But the other, what Bargmann-Fock says is that you pick a complex structure on M In other words, so then M. So then when you complexify, so if you take take things at M and throw in complex linear combinations of them, you're going to get M plus. And so this thing is going to look like, see that this looks like a d-dimensional copy of the complex numbers. It's going to have, let's say coordinate zj, and here is z bar j, and this is another copy, but related to this one by conjugation. That there's conjugation takes you back and forth. So this is what you get out of a choice of complex structure, and typically, yeah. So there's kind of a standard one that you normally use when you write the z's in terms of p's and q's, but and in the cases in quantum field theory, we're going to find also that there's going to be a standard one that you're going to use. But it's often interesting to think a bit about what happens if you change your choice of complex structure. And I haven't really emphasized that very much, but typically in quantum field theory, that tells you about some more interesting exotic questions about quantum field theory. I may say a little bit at some point, but mostly we're going to just we're not going to think about varying this. We're just going to pick a standard one. Okay. And now once you do this, this gives you, this picks out U D sub. Okay. So now, instead of looking at all kind of symplectic, all transformations of this thing, which preserve the structure, we can look at all transformations of this thing which preserve this Poisson bracket, but also preserve the splitting. Okay, and so now instead of so then what you're going to get is you're going to get things that are not just in here, but that are in here and that preserve the splitting, and this turns out to give you things that belong to a unitary subgroup of this guy. And this is, anyway, so the fact that this, let me just say that there. Okay, and so what we're interested in is the quadratic polynomial. So now, if we're going to try to get so we're going to have the same kind of situation. We're going to the moment map is going to tell us for any for any subgroup of here, for any subgroup of here, it's going to give us for each element of the Lie algebra a quadratic polynomial. And now so Lie SP to B R goes to quadratic polynomials, and now you can break these things once you have this business of z and z bar. You can think of things that are of the form, zj, z. The things that have two z's, things that have two z bars. And then things that have a z bar. Okay. And sorry, 3. Okay. So what actually happens is that the Lie algebra of the symplectic group, which has a basis, which is all of these guys, it breaks up into kind of 3 pieces. One piece which is these guys, another piece which is these guys, another piece which is these guys. Now, so what's going to happen is we're going to then quantize, and these guys are going to have 2 creation operators in them. These guys are going to have 2 annihilation operators in them. So these guys are going to kind of there's going to be some kind of overall quantum number you can associate to states. These things are going to add 2 to it. These things are going to subtract 2 to it. But these things are going to keep it the same. And it turns out that these guys, you can also show that. Well, let me say that these guys give you the these guys span the Lie algebra of this unitary group. Okay, so what happens? So we're going to be interested in. We're not going to pay much attention to these things. These things, these are symplectic transformations that when you quantize them, they kind of move you up and down between energy levels of the harmonic oscillator. These things, when you quantize them, are operators that keep you within the same number of quanta of your harmonic oscillator. And when we go to quantum field theory, we're going to be interested in it's typically these operators that we're going to be interested in. The symmetries of the theory that we're interested in are generally going to conserve. They're going to conserve particle number. Okay, so we're interested in what we're interested in is generalizing these guys. Okay, so let me then.
Sorry. Yeah. For the third one, like, is it similar as like having z and then differential, like derivative with respect to z? Like.
Well, okay. So yeah. So when we actually let me I'll start to explain these some more. But in one thing, when we quantize, this guy is going to be multiplication by z, the creation operator. This guy is going to be differentiation by z. So there's going to be no net change in the total in the degree of the polynomial. If you start with the polynomial of a certain degree, this won't change the degree. It'll move the code. But let me. But anyway, so it's these guys we're interested in, and maybe another thing, and maybe a better way to think about them is that let me start writing down the rest of what I want to do. So I want to kind of get some formulas for how these guys act, and that if I've got some kind, what I'm looking for is really what I'm looking for ultimately is to be able to do this. I want to pick. I want to find a symmetry for us is going to be some subgroup of the symplectic group. It's going to be some subgroup of things which preserve the Poisson bracket. In a quantum field theory, it's going to be things like translations of the fields in space-time, or some kind of internal symmetry transformation on the fields, or it's something, but it's something that preserves the Poisson bracket. But it's some finite dimensional group, some much smaller group that preserves the Poisson bracket. And the thing to watch out for, to notice, is that when I try to do this in the case of quantum field theory, d is going to be going to infinity. So this group becomes very, very kind of hard to think about, but there are going to be some finite dimensional symmetry groups inside it, which we'll see, which are the ones we're interested in. Okay, let me get to yeah.
How do we pick out a UD subgroup out of the symplectic group? I mean, is that UD of the elements that commute with the complex structure J?
Yeah, exactly. Yeah.
Yeah, but I mean, is there any other way to pick this out, like in chapter 24 and 25?
Well, I say a lot about. There's a lot of material which I wrote down in the book about complex structures, about how to think about them and what they are, and some examples. I don't want to actually. It turns out that that whole stuff I think is very nice, but that actually doesn't. In the end, that isn't actually what we're going to need later. What we're just going to need is specific complex structure. Okay, but anyway, there is a so you can define this UD is the subgroup of G's. Yeah, it's a subgroup of G's that are inside here, such that the G J is equal to 0. So I mean, yeah, I mean, the complex structure is given by some, by some map of some linear map of the phase space to itself that squares to -1. And then if you look at all look at all linear maps on the phase space that commute with this one, and you have to do a little work, and then you can show that those G's in here that satisfy this condition give you the unitary group. So that's an abstract way of thinking of it. But you can also do it very, very explicitly. So what we'll see in a minute in terms of polynomials very, very explicitly is in terms of polynomials very explicitly, if you just focus on these guys, we'll see that you can identify these guys with the Lie algebra of it. So it's a very concrete condition at the Lie algebra level. Okay. What? This is what I want to say. Okay, so what we do is so we take. So what we're going to do is we're going to pick a element of the D, and actually it turns out that the we can. If we're just going to be thinking about the space of we want to identify this guy with quadratic polynomials. I mean, we don't. There's going to be some condition that if you think of this as a matrix, there's going to be a condition that it's an anti-Hermitian matrix that makes it an unitary. But you might as well just allow any kind of complex. It's just as easy to allow any kind of complex coefficients times this guy, and only kind of worry about the unitarity condition at the end. And then if you complexify, it's the Lie algebra of GL B. Okay, so this is anti-Hermitian. So this is all complex D by D matrices, and so it's easy to just work with these guys. This inside here is the anti-Hermitian, is the A is equal to minus A dagger ones. So but the calculations we're going to do, you might as well just work with any on the Lie algebra of all D by D matrices. It's just easy, and then you get a story about how this guy works, but this guy, if you try and reinterpret this in the language I've been talking about, this guy is a well, anyway, this is not going to give you unitary operator. When you quantize, these things in general are not going to give you unitary operators. If you want to get unitary operators after you quantize, you have to be in here. So anyway, but I'm going to write formulas. I'm going to write down some formulas right now, where A is an arbitrary matrix, and you should think of it as being in the Lie algebra of the linear group. But you can so the ones satisfying this condition are going to be the ones that we're ultimately interested in. But we're just doing it for all matrices right now. And so what you want to do? So we want to know, given a matrix here, what's the quadratic polynomial that the moment map tells you? And the answer is just this: is I sum over J K Z J. Okay, so it's just this way. And so one thing I was doing in these other sections was just kind of showing that this is the correct moment map, and but the idea is that this gives you a nice kind of nice formula relating elements of the algebra of what's going to be your symmetry group to to quadratic functions, which are the things that you're going to quantize, that are going to give you your your conserved quantities and your corresponding your operators. So this is the fundamental construction, and it has this nice. Anyway, it has this nice form. And then what you do is you can show, and this is what I kind of work out in gory detail in the section, that these guys, this is the moment map, because what it does is you so this. These really do, these quadratic things of this form, really do sit inside the all the you have a big Lie algebra of all functions with a Poisson bracket. Well, if you look at these quadratic functions, they satisfy this, so they actually satisfy the right relation. They satisfy the Lie algebra relations for for this Lie algebra. So they satisfy it. Okay, so this is one thing. But then the other thing is what happens. Okay. So this is about what happens purely in this kind of this story about how these quadratic polynomials interact with each other. But there's also a story about how the quadratic polynomials interact with the linear polynomials. Because remember, there's this abstract nonsense I was trying to sell you about how you have a what you have is you actually have a Heisenberg Lie group acting, and you have a semi-direct product of that with the symplectic group acting, and the symplectic group is acting by automorphisms on the Heisenberg Lie algebra, and at the level of Lie algebra, so this kind of means you have a semi-direct product of Heisenberg and symplectic, and at the level of Lie algebras, you have not just quadratic is quadratic, but you also have quadratic, and then linear is going to be something linear. And the things that I so if I wrote if I write. I'm writing z vector is just this column vector z1. So okay, and then similarly for z bars. So what happens to well, you get these formulas. Actually, maybe let me just write these out this way. If you take this vector and look at the conjugates, and you take this vector itself. Sorry. So this is D components here. This is D components here. What you get is you get the A transpose conjugate acts A transpose. E vector bar. So I'm writing this down. I just to see what this guy does to any kind of linear thing. I got to see what it does to the z's and what it does to the z bars. Well, I'll put all the z's together into a vector. I'll put all the z bars together into another vector, and now I've got a 2D vector of these objects. And to see what this guy does to those objects, what the formula you can work out is that it just multiplies these, it takes as you want it to, it takes z bars to z bars, and it takes z's to z's, and it does it by multiplication by the transpose conjugate of A on the z bars and by the transpose on z. Anyway, so this is just the okay. Okay. Anyway, so these are kind of the basic formulas that we're going to. This is kind of the basic formulas we're going to use. So the idea is that at least at, at this kind of classical level, anyway, yeah. So basic for the moment we're going to use this thing to any kind of any kind of element of the Lie algebra of the group that we have acting on our system. We're going to associate this quadratic thing in the z and z bars, and what it's going to do, what this on the coordinates is going to be this, and so this is how the symmetry. Anyway, this is how the symmetry infinitesimally acts on the coordinates. And so maybe what I should do then is take is just then quantize. Okay, and so then the way quantization works is just this. Is just a okay. So what do we got? We've got z. Okay. So the way quantization is going to work is basically all of these z all these z and z bars are just going to become combinations of annihilation and creation operators. And if you want and those can be realized explicitly as multiplication or differentiation operators on polynomials in the z's, if you want, or you can just think of them as abstract operators satisfying some kind of commutation relations. But the formulas corresponding to all of this are gonna come from what you have to do. Okay, so you take z. What is it going to be? Zj is going to go to a dagger j, and again, and so you have to watch out. So in order to kind of keep straight the question of what's in order to keep straight the question of what's how to preserve unitarity of what's Hermitian and what isn't, you have to make sure you have the right factors of I. And in the way I was doing this here, you always when you go from the classical to the quantum, the standard convention is to put in a factor of minus I, because that gives you that's due to the fact that we want our q's, our q and p, real q and p variables we want them to turn into we want them to turn into Hermitian, into the standard operators that physicists use are Hermitian operators. We want them to think of them as giving a Lie algebra action, so anti-Hermitian. So they're I's that you have to keep putting in. But let me see if I've got this right. So then you've got then z bar goes to the minus I. So the z bar becomes the differentiation, the annihilation operator, and then you've got zj. Okay, so I won't. So zj. So these guys are pretty are fairly straightforward in the sense that again it's a minus I, and then you can put AJ dagger. You can do the same thing. And here, the nice thing which is happening here is that it doesn't matter. These operators commute, so there's no kind of operator ordering problem here. These you can these two commute and these two commute, so you don't have to worry about the order of things. Okay, so the problem, and then I won't write down. There's a similar one for z bars, but the tricky one is this one: is what to do if j is equal to k. Oh, and I guess I could also do so j is not equal to k. Then what I'll normally write this down as zj zk bar 1 goes to minus I AJ dagger AK. But again, if j is not equal to k, these things commute. So it doesn't matter. It doesn't matter. I can also write it the other way. But now,
question, like, why is it not linear in the sense that like why should there be a factor of pi for the quadratic like z, j, zk?
Well, you just have to. I mean, the factor of I is just keeping track. Is really kind of just keeping track of, where within the space of all the things we're looking at. What are the what's anti-Hermitian and what's the unitary things. So it's not. You might guess that when you multiply two of these things together, you multiply the two i's. But you can easily see that that's going to change. The point is you want this guy to become. It's a little bit. Well, maybe a good way to say this. Here's what I need to do. Okay, if I take some combination of z and z bars, which is real, that if I conjugate it, I get the same thing. That should become real. That's in the real Lie algebra of the symplectic group, and that should become an anti-Hermitian operator. Okay, so the point is I have to take I have to set this up so that polynomials in z and z bar that are real, that when you complex conjugate the polynomial you get the same one, that those are self-adjoint. Okay, so I got to have that. No, that those are skew adjoint, because those are, so if you want to enforce that condition, this is one way to do it. Okay, does that help?
Yes, sir. Actually, is this related to the fact that the Poisson bracket of B and Z bar is I, and while the Lie bracket of A and A dagger is 1, so we have to multiply by 1 to preserve this condition.
It's the same thing. I mean, that's the same phenomena at the level of the Lie algebra of the Heisenberg group. Yeah, it's exactly the same thing. But I mean, it's kind of confusing here because the problem is when you're working with P's and Q's, then anything you do with them is real, and then normally physicists like to get self-adjoint operators out of them, and then physicists have to start throwing in factors of I in order to get. And anyway, that's the normal problem. This problem is just a little bit more confusing because these guys are not real. They're I've complexified, so these guys are not real, and these guys are not self-adjoint. But you want anyway. Yeah. Okay. Yeah. Anyway, there are a lot of ways of seeing this. Another way to see it is try to do it the other way, and you'll quickly see things don't work. Yeah. But it is, you're right. It's the same I that's showing up in the it shows up in the classical Poisson bracket, but not in the commutation relation. Okay, but now let's see. Let me go to quickly say something about the. So now this is where it gets tricky, and I'll say some more about this. I think next time about some of the troubles this leads to, but. Okay, but then Z, if you take Zj bar, what are you going to associate to it? Okay, well, it turns out that the there's really two possibilities. There's minus I A J. I guess I have. There's a half AJ, a J dagger, plus a J dagger, AJ, or there's minus I AJ. AJ. Okay. These are the possibilities. So this guy. And this guy is the same thing as this guy is the same as minus 2 AJ dagger. Oh no, wait a minute. Sorry, plus. And it's not You can use the commutation relations to show other way around. Okay. Okay, so you can so there's two possible things you can do, and they're actually not the same. They differ, but they differ by the scalar. And they and this is actually the scalar which in the end is responsible for the fact that the energy of the ground state of a harmonic oscillator is a half, not zero. Okay. So another way of saying it is going to be, we're going to want, the standard Hamiltonian we're going to take is going to be the sum over J of these guys, and that's and this guy. Anyway, so this guy has the nice. Okay, maybe the thing to say about this is to give this one and two. Okay, one, you have nice satisfies the sp2d the u of d are bracket relations. So there's some sense in which this is the right one, if you like. There's that this kind of group theoretically this one really is the right one. But what am I trying to say here? Okay, but I think maybe I better say more about this next time, because I want, this is kind of a subtlety which appears later on in quantum field theory in interesting ways, but we're mostly going to avoid it, and so we're mostly going to use 2 instead. And this is called the normal ordered form. And so sometimes if you have you'll see sometimes if you have an operator, and if it can be written in terms of some combination of these guys, if you put this symbol in front of it, what this says, it means is put all of the annihilation operators to the right and all of the creation operators to the left. So to move it that way. So these are the these are what are called the normal ordered version of these operators, and this is what I'm going to actually use. So what's going to happen? So this will have. Okay. What's the right missing? Anyway, let me say some more about the subtleties of this next time. But we're actually going to. So we'll use these. So these have simpler behavior, and especially in QFT, especially in quantum field theory. Okay. So all of these. Anyway, it'll be a continuing problem, but it turns out that you actually. Work it well. Anyway, well, you can kind of see it here. Working with these operators and always in the strong ordered form, actually these things have a lot of kind of nice properties, and I want to kind of stick to. We'll mostly be using them, but you have to watch out that they're not Anyway, let me say more about the subtleties of this next time. Okay, so I'll just say that for now we're going to use this, and so I'm going to write down these formulas. Then is that we're going to write down. So we'll use A goes to U A, And so I'll write it as a Lie algebra representation. It's UA prime. There is some. Anyway, so it's giving. There is some kind of. There's some representation of this unitary group UD, and that this guy there's a Lie algebra representation, and the operator that you're going to get for a specific element of the Lie algebra is this guy, is the sum over JK. Okay. So this is going to be our main formula that we want to use. And so, so anyway, this is what we're going to be. What we're going to be doing. We're going to ultimately, for every, if we have a group of Lie group of symmetries, each Lie algebra element, which is going to be given by a matrix, is going to be given correspondent to this quadratic operator. Okay, and what these things are going to do is they act on the Fock space, which you can think of as a space of D harmonic oscillator, the state space of the D harmonic oscillator. They preserve the total number of quanta, so they kind of move you around the states with a fixed number of quanta, or which corresponds to, with a standard Hamiltonian to a fixed energy. So these are the operators we're interested in, and we're going to be, and this is what we want to actually generalize to quantum field theory. In quantum field theory, what I'll get to later is these A and A daggers are going to become these A and A daggers that depend not on an index J and K, but on a momentum P, the ones that I talked about before. Okay, and that's or in X space they're going to correspond to fields and adjoint fields. But anyway, but then the relations just then these I guess I erased these relations, but you have the same kind of these commutation relations that you have that this guy anyway. So these guys, if you take the if you take the commutators of these guys, you satisfy the relations of the anyway. You just get the commutator of the matrices, and then you also. I mean, I shouldn't get into this. Where was I doing this? UA, and then a dagger. Let me call the vector. So it's going to be it's a column vector of the AJs is going to be given by A transpose. So and here. It's just I just made a column vector out of these, and then this is how this works, and this is true for any this actually works for any, as I said, this works for any matrix A. These formulas work, and they give you a Lie algebra representation of GLD the complex. The Lie algebra of GLD, and if you decide to choose these to be anti-Hermitian, then you're going to get things that that are in the Lie algebra of U of D, and those are the things that on the Fock space are going to act by unitary transformations, whereas these general things are going to act by linear transformations on the Fock space, but it won't. It's only be unitary if these are anti-Hermitian. Okay, so let me see what I want to try and get here. Okay, and then so then what happened is, I mean, the next part of the story that's in these chapters is I went through and kind of worked out in detail what happens in the cases D is equal to 2 and D is equal to 3. And let me just say a few words about it. and some of this was in your, what was that? So if you have two oscillators, so this corresponds to that too. You have coordinates z1, z2, or if you have two creation operators. Now, what these are going to do is so the overall so you're going to have a U2 that's P4R. Okay, and so any kind of quadratic, any kind of 2x2. So A is an element of two. It's a 2x2 complex matrices, and one actually, how did I want to choose that? I'm just going to be okay. So one A is going to be. I've got the A is going to be. I think it's a minus I to make it her anti-Hermitian, and then 1 1 0 0. This is going to quantum under quantization. This is going to be the thing which gives you A1 dagger. And that's the Hamiltonian. But again, I mean, it's the normal ordered version of the Hamiltonian. Okay, so you've lost when you normal order, you lose these halves. Okay, but then so this gives you a so this corresponds to a U1 subgroup of U2. And then but if you look at the rest of the other directions, so you look at the directions. So this guy commutes with everything, but there's kind of three other complex directions in here, and in those other directions give you the Lie algebra of SU2. U2, and this construction is then you get the previous construction of reps of SU2 as polys in Z1, Z2. So this is now here. So A1 dagger is just multiplication by Z1, A2 dagger multiplication by Z2, and then A1 and A2, the annihilation operators are just differentiation. Well, this is exactly the story we went through, last semester about how do we get the repetitions of SU2? Well, you can get them by looking at all polynomials in Z1 and Z2, at all homogeneous polynomials in Z1 and Z2, and so I mean you have to, you want to kind of keep the same you want to keep the same number of these guys, and then you're going to get anyway the whole everything I've written down is just exactly a story that you've seen before about how to think about the representations of SU2. But the other thing that you can do is you can instead, or what's the other one you can do? What do I do? Or let me not. Anyway, let me not go. I mean, there's another case worked out in there you can look at, but this is the main thing I wanted to do with this guy. But now let's do d is equal to 3. Okay, so in d is equal to 3, again, you're going to classically have 3 kinds of z's, 3 creation and 3 annihilation operators, and you're going to have a U3 the complex structure is going to pick out a U3 inside SP6R. And so what you're going to get when you so you get, and again, the same thing, you have a U1 sub U3. There's the overall kind of phase. There's the overall phases which are in here, which you can get by taking the determinants of the matrix, if you like. Gives you an overall phase, and that gives you a U1 subgroup, and that corresponds to this guy. And this is gonna, it's the same story here. You're gonna get the Hamiltonian is A1 there. Okay. So you can get, you're gonna have this guy, and so this is the same. This is the story that we're always going to have in this kind of thing. That there's always going to be kind of an overall U1, which corresponds to just, once we've picked a complex structure and we've identified our phase space with a complex space, it's just overall phase transformation, just multiplying everything by e to the I theta. That symmetry is going to be a U1 symmetry, and the corresponding operator is going to, is going to be the Hamiltonian operator for the symmetric harmonic oscillator. Okay, then the other thing you can do is again look at look at the things with determinant 1 in here. So SU3, and this goes to again. So operators. So you're going to get 8 operators. Anyway, for various, anyway, so you're going to get a the possible 3x3 anti-Hermitian matrices are going to it's going to 8-dimensional space of those things. Oh, and with trace 0, so that the U1x trivially. Then you're going to get 8 operators that look like this, and you're going to get the same. You get the representation. You get the reps of SU3 on homogeneous poly. Let me just write it as on SRC3. Okay. So this is going to, of course, it's going to be a similar story to what happened in the in 2 dimensions, where you were looking at homogeneous polynomials in Z1 and Z2. Here you're going to get homogeneous polynomials in Z1, Z2, and Z3. It's going to give you more. It's going to give you some irreducible various representations of SU3. Unlike in the SU2 case, you can't get all of them this way, it turns out, but it gives you some of them. And physically, what these things correspond to is, the state spaces of the harmonic oscillator with various numbers of quanta. Okay. Just as the SU2 representations with different spin, you're going to get by looking at the state spaces of this guy with various numbers of quanta, you get the same thing here. And then maybe the last thing to say. Okay. The other thing is we can in three dimensions there's another kind of interesting thing, because you also have SO3 inside SU3. So you can look at things which are anyway. So you can look at the things which correspond to, if you break your phase space up into P's and Q's, it corresponds to things which separately rotate you in P and Q, preserving the length in Q space and the length in P space. And this gives you the anyway, these give you the so here you take, for instance, A is equal. This is something A is equal to. It's going to be one of things of this kind. it's just going to be a three. It's going to be a 3 by 3 real matrices that are antisymmetric. So, for instance, e.g. L1 is 0, 0, 0, 0, 0, 1, 0, 1, 0. If you take that real matrix, which is and then you have to take, okay, then you have to, well, you have to keep your eyes straight to when you quantize, get something that's her mission, and you're going to get the you get UL1, right, and I think I wrote this down, so it's a sum and 1 to 3 of a dagger, and then LJ, L1, M, N, anyway, it's gonna, you can multiply this out and see which, I think I actually wrote this thing down. So for instance, so it's like what is it? It's A3 dagger A2 minus A2 dagger A3. And what this is this is just exactly the angular momentum operator. This is, again, well, this is anti-Hermitian, so it's this guy, L1. So it's the angular momentum. So you can also see this. You can also see these angular momentum operators that you have whenever you have kind of a rotationally symmetric problem in quantum mechanics. Well, this is a harmonic oscillator is one example of it. Well, it's going to correspond to the fact that there's inside this bigger SU3 group, there's a group of things which just rotate separately, the P's and Q's, which correspond to physical three-dimensional rotations. And then if you apply this nonsense I've been telling you about, you find that this is the you find this formula for the and this is the formula for the angular momentum about the one direction in terms of these operators. If you rewrote everything in terms of P's and Q's, you would just get back the old formula you're used to about the relationship about what's the angular momentum operator in terms of P's and Q's. Okay. But this is one version. Okay. Anyway, so let me stop with that and okay. Let's see. One second. Okay. Okay. So now let's get. Let me quickly. So now what I want to do is I want to just kind of take this whole picture and move it to infinite dimensions and use it to write down to figure out what the symmetry operators are, what operators we're going to get corresponding to symmetries when we try and do quantum field theory. So I'll work out more of this next time. But let me kind of just say what the translation is going to look like and what happens when we do this. Okay, and then the first thing I'll do is I'll start talking about the Hamiltonian and dynamics. Okay, so let's see. So this is anyway. So now we're going to leave finite dimensions, but you could. Okay, so on to Q of T. Q of T, and this is really, and the idea is it's going to correspond to D goes to infinity. So it's going to be, if you want, as I said, you can put in lots of cutoffs, and then you can think of this quantum field theory as an example of this whole of this harmonic oscillator formalism, but for D some very large number. But then you want to take ultimately you're interested in what happens as you take the number of degrees of freedom going to infinity, or as you take the possible number of x values or the possible number of p values up to infinity. But let's see. So what we're going to do is now we're going to take m instead is going to become what I call H1, which is the solution to the Schrödinger equation. Well, so the free particle. Okay. And then now what we want to do, so one thing to notice about this is that we have that you have this inner product that psi1 psi2 is equal to the integral, you know, and again, it'll always be one spatial dimension for now. So psi1 bar of x, psi2 bar of x, dx. And the point is that we can think of these as being complex valued functions we can think of this space as being labeled by complex valued functions of x at a particular time in the initial data for your problem, or we can Fourier transform and work with the Fourier transform data, but it's the same formula then. But either way, it's the same standard Hermitian inner product on functions. Either and Fourier analysis is set up to make these guys equal, and the Fourier transform preserves this inner product. Oops, sorry. Okay. Yeah, so it's anti-Hermitian, anti-linear on this side and linear on this side. Okay, so now what you can do, what you can do is that this gives the imaginary part of the imaginary part of this guy. So you can figure out what the imaginary part of these guys is. Take this plus the conjugate minus the conjugate divided by 2i, and you'll find out that this is omega is some anti-symmetric. This implies gives you a Poisson bracket. So the way that you get kind of the standard story about a phase space, I said that you could think of this guy as a phase space. Well, you need a Poisson bracket. Well, the Poisson bracket is just given by looking at the imaginary piece of this. Okay, and actually also notice that the real piece of this is symmetric. And used for fermions. And as I said, I should have said as I was going, everything that I told you so far about bosonic quantization, exactly the same formulas work for fermionic quantization as long as you turn commutators into anti-commutators. And then so it's the same thing. If you can write down a fermionic quantum field theory of kind of fermionic free particles satisfying the Schrodinger equation, and you start by taking the same space, and the only thing you do is you use the real part of the inner product for a symmetric bilinear form, and that's going to give you standard anti-commutators. Okay, and but now, okay, so something to notice is that what preserves this in some sense is some kind of SP infinity here. What preserves this is some kind of O infinity, if you like. These are infinite dimensional spaces. But the problem is these groups are much too large to kind of usefully think about. But what we're interested in, and then U infinity, the intersection. So the intersection U infinity preserves both. Okay, and we're interested in so we're interested in groups G that are inside of this U infinity. Okay, so all of the symmetry groups that we're interested in, the reason that they're symmetry groups and that they're interesting is that they act on the space of free particle Schrodinger solutions, and they act preserving the inner product. Okay, and so they preserve both the imaginary part and the real part, and so there are unitary transformations on here, but we're not going to, but we're going to be interested in kind of much smaller groups than these things. So we're going to be interested in things like, and anyway. So we're next time well anyway, starting in a minute, we'll start working out a lot of different groups of this kind, but they're always going to lie in here. I mean, they're always going to be there. The reason that there are symmetries in the situation is that they're symmetries. They preserve the free particle Schrodinger solutions, and they preserve this inner product on them. Okay, so now what do we do? So now the idea is that we just want to take all the formulas that I wrote down with before, and I want to change them into quantum field theory formulas. And so what we want to do is just this. Okay, so now the index. So in the finite dimensional case, we had an index j that took some finite number of values, and this is going to go to either to x or p. Okay, so there's always going to be, we can either do things in momentum space, or we could do things in position space, and we have this and the Fourier transform is going to take us back and forth, and if the so what's indexed? What we used to have a j that indexed our zj's and our annihilation creation variables operators. Now they're going to be indexed either by x or by p. Okay, and so this is going to be so zj is going to go to psi of alpha dagger of p, or what did you say? Yeah, just say p or x, p or x, alpha p or psi dagger. And so the quantization, yeah. Oh, sorry. Yeah, it's just going to be these. So thinking of these as being sorry, alpha p psi of x is this, and then under quantization. So the quantization of these guys, which is going to be these guys, is going to go to these operators, a dagger of p and or psi hat. So the analog of what we're going to be doing continuing is we're going to be writing down. So what we want to do is, before we had these formulas that gave you quadratic things in the quadratic things in the ZJs, well, or in these operators, we want to write down quadratic things in these guys, and our problem is going to be that, remember, and that sum over. Remember, we were summing over j and k, okay? And this is going to go to, in general, it's going to be some double integral, but or a single integral if a is diagonal. Okay. So if the so often what we're going to do, if we want to exactly solve our problem, what we want to do is we often want to find a basis in which these a's are diagonal, and then the only instead of summing over the aj, anyway, these sums, then instead of having two sums, there's only one sum because it only have things in the diagonal. Okay. Now let me, what did I want to do here? Let's see. Okay. Okay, so let me start on the next part of this, which is okay. So we're going to do kind of a simple, kind of crucial
So you
example.
mean A is diagonal or diagonalizable?
That you've actually chosen in diagonal in the well, maybe just to say what I want, and maybe I'll just show this in a minute. Maybe let me just say what I'm going to do in a minute. Maybe that'll make it a little bit clearer. That okay. So what I want to write down now is the so G is equal to R, where it's the group of X on H1 by time translation. Okay. Now so what you're going to get. Okay. So the output of all this. So here the lead G is just R. So there's going to be kind of one direction here, and you're going to want to produce one operator, but that operator is the Hamiltonian. So this gives ultimately the Hamiltonian. As a quadratic in a dagger or psi dagger. Okay. So this is, I mean, kind of in some sense the in some sense the simplest and most basic aspect of symmetry is that we're quantizing a space of free particle solutions, and so we know how they act when you translate in time, and so translation in time preserves that inner product, the standard inner product, and so it should, by the whole philosophy I've developed, it should correspond to a quadratic an operator in the state space, which is quadratic in these quantized objects. Okay, so let me kind of running a bit out of time, but let me kind of then very quickly tell you how to find this thing. Actually, maybe let me write down the let me first just kind of write down the answer. I mean, the answer in some sense is more compelling than the derivation, but we'll see. And then this may answer your question about the diagonal. That's right. So here we'll find equal to the integral dp p squared over 2m a dagger of p, a of p. And so what this is, so physically what this is saying is that for each, so imagine that there were only a finite number of possible p's. Well, this is the number operator in quantum mechanics. This is the thing whose eigenvalues tell you how many quanta you have. So what this operator is, it's basically summing over all the p's and giving you the number operator, and then multiplying by the energy of a free quantum, which is p squared over 2m. So physically, this is what you have to get. But remember, but here, what's happened is I've decided. So the operator here, in some sense, A, in some sense, is it's diagonal. So you're not. summing over different indices here and here, you're using the same index, but it's diagonal with kind of P1 squared over 2m. So it's just got P, anyway, Pj squared. So what I meant by the case of a diagonal case of an operator is this thing, the operator that generates these translations in time. It's the thing with but because it's diagonal, you're not going to have two integrals or two sums. You just have one sum over the diagonal. But this is in P space. So I've gone to I'm working in P space, and in order to anyway, the fact that I'm working in P space is what's diagonalized this operator. If I were in X space, then you get it. Anyway, let's see what happens in the what about, okay, now let me then just, because time is getting short, let me just kind of write down a few formulas. Is that you find okay, so for any operator you get the Heisenberg time evolution by ddt. The operator is the operator at minus I. So this goes back to what I tried to tell you last time, that when we're going to work with these theories, well, the way we're going to work with them is we're going to work in the Heisenberg picture. We're going to work where the dynamics, you understand the dynamics by understanding not how states evolve. You just kind of fix the states as to like what they are at time t0 or something, and then you look at for any operator, you look at how it evolves in the Heisenberg picture using this, and then so that I kind of did get that last time, and then this implies that the as the a dagger ddt. Okay, so one kind of operator is going to be these annihilation creation operators. Dagger dt is going to be H. Okay, so you can use this guy. So one kind of calculation you have to try and do and see if you can understand how to make sense of this is to use the annihilation, use the commutation relations for the A and A dagger to calculate what happens when you do this. If you commute this with this guy, and so you have to try to make sense of this. And again, I mean, the simplest way of trying to make sense of this is to think of all of this as P as being a finite index, and then you can use the standard discrete commutation relations to see what's going to happen, and you'll find that this does turn out to be P squared over 2m. Sorry, yeah. So this is then I times P squared over 2m a dagger. P. And so you find, so this implies that a dagger of PT okay, so this is the anyway, so this is the kind of solved dynamics of this problem. That if you just stay in P space, the only interesting operators are these A and A daggers, and the way that they're going to behave. If you know what they're doing at a given time, which is that they're just adding or subtracting quanta onto your states. Well, what they're going to do at later times is they're going to have the same behavior, but just with these phase factors, which depend upon p. So this is the dynamics. Let me see. I wanted to do one more thing. Okay. Okay. And then notice, okay, so maybe then then now you can do the same thing for okay, so let's do this for the field operators. Okay, so what? Anyway, so I won't try and work out this calculation, but what you want to so you have to, if you want to understand this calculation, you basically Fourier transform everything that's in this calculation, and what you end up learning is this kind of thing. You end up with H in X space. You're integrated over X space, but you have a m d squared dx squared. Okay, so this is just this Fourier transform of in P space. I had I had a dagger of P and then a P squared over 2m and then an A of P. Well, if I Fourier transform, the main thing that happens is the P squareds become minus I I ddx's, and you get this operator. So, but you can think about, the point is that you can think about this operator the same way as in this finite dimensional case. You can think of it as being, you've got these operators, you've got and this is some kind of infinite dimensional version of an A operator. It's but now in X space it's a differentiation operator. So it's only really diagonal in P space. In X space, it's kind of taking, infinitesimally nearby X's to each other. Okay, you have that, and then okay, and then what you find is that the solution to this then becomes, the solution is that this guy satisfies d dt psi dagger of xt x squared psi dagger. Okay. And what you'll find is that this, if I've got this right, yeah, this is actually the conjugate. This is the conjugate to the standard Schrodinger equation, because you're anyway. Anyway, maybe I'll say more about this, how this works out next time. But it satisfies this, and the solutions are well, one way to write the solutions for this thing, or to write this as 1 over the square root of 2 pi, are to write them in terms of Fourier transforms of these solutions. So you write them as e to the integral from minus infinity to infinity, e to the minus I px, e to the I p squared over 2m p, a dagger of p. And so this is, And by this I mean a dagger of P. And when I write a dagger of P, I mean it's the time dependent one at time 0. Okay, so let me stop so much. Say a few more things. This is the so this is the sort of formula which you'll often see in as often kind of a definition of a field operator. So if you take a quantum field theory class, what you often see is people start playing around with annihilation creation operators for quanta, and then say, well, the field operator, you know, the time-dependent field operator is, you know, is an operator that satisfies this equation for operators, and its solution in terms of these annihilation creation operators looks like this. So this is kind of the standard. This is often kind of given actually as the definition of what a quantum field is. And again, I mentioned last time that this is you know, I mean, and there's a similar one for psi itself for the annihilation operator, just without just the adjoint of this equation. Or if you have real fields, then you have a combination of this and the other one. But we'll get to that later. Let me start now. Maybe just a couple last comments was about okay. So so this is the free field theory. But now, if you want to start to make this an interesting, physically more interesting, there's two things you can do. So generalizations. So particles in a potential. What you can do is take h hat is the integral minus infinity to infinity here of x minus 1 over dx squared plus d of x. These are all. Okay. So if you wanted to talk about a kind of an external field problem where you've got arbitrary numbers of quanta particles running around, but they're interacting with some kind of potential, then you can just change the anyway. You're in principle you still have a quadratic operator for the Hamiltonian. It's still this guy, and particle number is going to be anyway. So you still have this. The only problem is that you no longer know. Your problem now is that you no longer have control of knowing what all the solutions of the single particle equation are. I mean, you still have a single particle state space which you're quantizing, but it's not. You'd have to know all the solutions for this in terms of this potential in order to have it more explicitly. So that's much harder. And then interactions. I want to just so maybe we say this add. If you add a term that looks like this, and psi. And so this is a function. This is some kind of, maybe let's make it just depend on the difference between the positions. So this is just some kind of function which tells you what the interaction what the what potential energy, what's the potential you get from one particle causing it on another. So what this is saying is that anyway, this is basically what happens if you, anyway, this is the expected change in the energy from this case, if there actually is some kind of an extra piece of energy you get from interactions between the particles. So if you want to talk about not just kind of free quanta running around, but quanta that actually can interact with each other, and perhaps by interaction strength given by some function v of x, then you can write it this way. And your problem with this, though, so this is what I'm not going to. This problem here involved quadratic field operators, and in principle, the methods that I've been talking about in this class have something to say about it. This is where you start. This is where kind of a standard quantum field theory class really starts to get started, because now that you have a quartic, you've got this quartic thing in the size. It's everything that I've been telling you about how there are these nice underlying symplectic transformations which tell you what's going to happen, that's now no longer true. The fact that this is kind of quartic in the size, and again, there should be hats here. So. The fact that this is quartic means that the methods that I've been talking about in this class really don't help you, and you need a whole new set of methods in order to try to do anything, and that's where you get started in a normal quantum in a quantum field theory class that's serious. Okay. So I think this was just kind of meant to connect this to see what you have to do to start to get more interesting physics. And what I'm going to do next time is go back to go back to our free particle problem that we really know how to deal with, and start kind of going through all of the kind of standard kind of symmetries that you know about, and look and see what kind of operators we get. So that means the typical kind of symmetries we'll be talking about are kind of symmetries of phase transformations, or symmetry or translation symmetries. The translation symmetries in space will give you a momentum operator. You also have rotation symmetries in space. They'll give you angular momentum operators. And so all of the kind of, they're going to basically give you versions of all of the operators that we knew about on the single particle space, about what they did to a single particle, but they're going to give them to you in a form where they act on the whole multi-particle Fock space, and they act on, anyway, on this entire theory of multi-particles, not just a single particle. Okay, so maybe better stop there for now, but any questions about this stuff, or no? Sure. Yeah. And I should say, yeah, so the well, yeah, anyway, I may go back and pick up there. There are a few things I didn't really have time to. There's some confusing aspects of the story that I didn't get to in this discussion today, which I think are reasonably handled in the book. I mean, maybe just one thing to watch out for is there's a really tricky issue of the sign here. And if you think about this, if you think about what's happening in the and it's really because you're in the Heisenberg picture. If you're used to how states evolve in time, and then instead you're talking about how operators evolve in time, there's some kind of, anyway, in some sense, if you want to know what an operator is doing at a given time, you have to kind of move it backwards in time to time zero. And so there's a minus sign which comes in it, which is confusing at various points. But other than that, I think the formalism for the free particle should be relatively straightforward. And I spent a lot of time in these notes kind of, working everything out kind of classically, and then doing the quantization and going back and forth. And it can look a little bit confusing, but it really is just, it's just exactly the It's just exactly the same thing as the harmonic oscillator formalism, the Markman-Fock formalism, except with this infinite dimensionality problem to worry about. The fact that you've got this extra structure, and you have to continually exploit the fact that yes, you're in infinite dimensions, but by using the Fourier transform to go back and forth between X and P space, you can often, what's a complicated operator can become a diagonal operator if you Fourier transform it, and then that allows you to kind of keep under control what otherwise would become totally out of control problem of the fact that you're in infinite dimensional space and you've got linear operators in infinite dimensional spaces. Okay, so any other questions now? Okay, well, if not, so I'll shut this off. But please do come back. I'll be around for a while. And if not, if I don't see you then, I'll see you on next Tuesday. Bye.
Thank you.
Thank you.